my name is Scott Smith, and I'm going to answer a few questions about the Gibbs and Helmholtz free energies. First, what is their meaning and what are they? Second, what is the difference between them? And third, when do we use one or the other? To discuss what are they, we need to talk first about an everyday potential in real life. So a potential that you might be fairly familiar with, or at least I hope you are, is gravitational potential. So if I raise a box to some height, or I change its height, I have given it gravitational potential energy. Similarly, if I have an electron and I have it in a wall socket, one side might be positively charged and the other side might be negatively charged. And this electron might have a tendency to migrate to the other side if I but connect those two sides. Similarly, the box would fall if I were to let go of it. And the energy would then be released usually into heat, but it would also be vibrations and in sounds and other stuff like that. And so these two potentials, gravitational potential and electrical potential, they tell us how our system has stored the energy. And we can learn things about how the system will evolve by minimizing these various potentials. Similarly, we have thermodynamic potentials, and these thermodynamic potentials are useful in a number of different situations. Because we first have, looking here at this equation for the change in internal energy from the fundamental equation of thermodynamics, we have this heat term, which is both of these terms here, Q, and we have the pressure volume work term, which is negative PdV. Further, I should have written this other work, or W squiggle. I'm just going to refer to other work as W squiggle. And these other forms of work might include stress strain work, or a battery reacting. There's all sorts of different types of work that you can talk about. And in different situations, when we might have chemical work from charging a battery, we might be interested in relating that to the change in internal energy. But that brings us to our next question: is when do we use these different potentials? And I should say, Helmholtz free energy and Gibbs free energy, just like internal energy, are also thermodynamic potentials. So when do we use one or the other? And it comes to this idea of natural variables. When I'm talking about a change in gravitational potential, or when I change the height of an object, I've changed its gravitational potential. And thus the natural variable of the gravitational potential is height. But when it comes to internal energy, if I knew how the entropy changed and the volume changed, then I could relate how the internal energy is changing to those two changes. And so we see that internal energy, its natural variables are entropy, S, and volume, V. And so if we knew how a system behaved with entropy and volume, then it would be very easy to track the internal energy. Often, however, it is much more convenient to talk about pressure, volume, and temperature. And the two thermodynamic potentials that are most frequently used to talk about pressure, volume, and temperature relationships, and I should mention these other forms of work often, or pressure volume work. The potentials that are used to relate those things are Helmholtz free energy and Gibbs free energy. And as I'm sure you have already pieced together, the natural variables of the Helmholtz free energy are temperature and volume, and the natural variables of the Gibbs free energy are temperature and pressure. And so in material science, we often see, because things are at constant temperature and pressure as they sit out on the lab bench, we might be interested in relating how the changes in their dipoles are related, or are going to evolve over time. And so we might minimize the change in Gibbs free energy as it relates to this, because there is no change in pressure and there is no change in temperature. Both of those terms are zero. And so we can directly relate a potential and the other form of work, and then we could minimize the potential and say, this is what will happen to this other property, or these other forms of work, as it tends towards equilibrium. Similarly, Chemical engineers often deal with situations where there might be a sealed vessel, so the dV is 0 and the temperature is constant. And so they could similarly relate Helmholtz free energy instead to work. And so that being the case, we use the potential that is most convenient. And that is always going to be the case. We're never going to just kill ourselves with math trying to relate things and adding these nonlinear terms when there's simply an easier potential to use. To summarize, first, the meaning of these potentials is they are potentials like any other potential, and giving you maybe a better grasp on their context helps you understand what they are. Second, what are they? Well, they are these relationships that I have written out. They are mathematical constructs. And then third, when do we use one or the other? We only use them when they're convenient.